Cool, and we're recording. Check, check, check. Okay, good. Just want to do a quick check here. Well, I got a new audio system. I got a Bluetooth audio headset, so hopefully the mic noise, the background noise in the mic, is going to be gone once and for all. Sounds clean. Good. Yes, thank you. If anybody hears anything, just send me a DM if there's any like background noise or any weirdness. I might have to break down and get a desk mic, but I'm trying to keep my desk like simple and clean, and this works for me. Okay, good, excellent, nice and crispy. All right, let's jump into things. Let me just kind of organize my windows here. Okay, so I've got a few things kind of planned. So I've given an overview the past couple times. I think I've done this twice, and then we had that one class where the Zoom servers failed, where that was the first class that I did this. So I think kind of 2.5 times that I've gone over the overview. I noticed I try to do it most classes, maybe not all, but I'll try to do it most classes or every now and again, to kind of give you all kind of, to me, that overview is sort of a roadmap. Like all the things that we're going to be covering in this course are set up to give you that sort of like a solid foundation, and you can go build on that foundation and learn all the other topics from there. It's not a comprehensive, view of everything that there is in Python by any means, but it's the what I think of as the core. And somebody else could argue that there's something else should be in the core or something that shouldn't be in there, but it's one way of looking at like a core set of tools to get you up and running in Python. So this time I just want to I want to treat it a little bit as a breakout. So do your best. I'm just going to put I think just 4 minutes on the clock. I might do less depending on how many answers we're getting in. But do your best to type out that overview. There's a lot of ways that it could go. You could put your own spin on it a little bit. It probably won't look exactly like mine, but what I'm looking for is those 4 or 5 main categories. There's one time where I broke it into 5 categories and one time where I broke it into 4. But at least those 4 main categories, if you can, or as many of them as you can. And if you can fill some of them out a little bit, that just involves kind of like the way that you would keep notes. So it's a bit subjective, right? It's up to you. There's not like a canonically right way that you must have it. So I want to do this, rather than you just listening to me talk about it. That way your minds are engaged and okay, what is in my core tool set and why might that be, right? And if you don't get all of them, you're not being graded. It's no worries. But I just want you to get thinking about it rather than just me talking about it. So on that note, why don't I put 4 minutes on the clock, and you all can write up a quick Python language overview, hitting those 4 main topics as best you can remember them. And then we'll go from there. Okay, 4 minutes on the clock. Okay, cool. The 4 main topics regarding the overview that that I've done a couple times before class. Oh, sorry. Perhaps there's a bit of a lack of clarity here. What I'm asking for is a couple times at the beginning of class, I've gone over an overview where I've talked about like 4 main categories that we're gonna cover regarding basic tools in Python, and it's meant to just give like an overview of what we're gonna learn and the basic language features and things like that. So the question on the table is, rather than me just going over the overview, I want to give you a chance to like think about it and recall those things. And if you don't have total recall over what those things are, then that's okay. And I've only gone over it a couple times, but I just want to get you all thinking about it. Also, if you don't remember anything, just how would you break up, the knowledge that you have? You can make up your own overview too. All right, cool. Get whatever your best approximation of that is in there. That's the end of the 4 minutes. I'm seeing a lot of really cool answers here too. This isn't necessarily meant, for you to get it perfectly right. So it's just I wanted to engage you all in thinking through this rather than me just talking at you. So cool. I'm going to go over the overview. I'm going to try to be really quick about this. And if you put in a few things that I don't include, this is a pretty subjective way of putting this together. And like I said, it's sort of built out of the way I view it and the way I kind of think. Like this is how I kind of categorize the information. You might categorize it differently. At the end of the day, it'll all contain the same information, though. It should. So you might break things up differently, and you might see some things that you might want to like kind of move around. But for me, I think this is a good way to just kind of contextualize everything and kind of give a sort of base foundation for how everything fits together. So the way I do the overview, we have our when we're going and learning. This is essentially what I do when I go and learn any new programming language. I'm going to learn about the data types. Abstractions, control flow, and iteration. Now you could give these, there's sort of, some of these have sort of synonyms we could call iteration, repetition. I think I misspelled that, but I'm going to accept it. We could call this loops, although that's a bit of a misnomer because loops are a type of iteration, right? So we'll flesh this out just a little bit. The data types that we've covered int and float. These are our numeric types that we've covered. Bool, which is technically a numeric type, but sort of, feels different, has a little bit of a different application than, what we think of as regular numbers, ints and floats, integers and floating point numbers. We've talked about strings, and we've talked about, I guess we've talked about none as well, a little bit, and we've talked about lists. For abstractions, we've talked about two main types of abstractions. We've talked about variables. Variables are pretty simple, right? It's just, this a equals 10 thing, and then if I print a, or if I perform some arithmetic operation with a will be regarded as the integer value 10, right? So it's just the ability to capture some data type value in a namespace, in an identifier, in a name, and we can use that name in lieu of the actual value. This is kind of nice because we could write a generic process that uses variable names when we don't know the values of those variables, and then we can go in and plug in the values of those variables, and then when the process runs, when it executes, it will use those values, right? So essentially, the reason this is abstraction is it abstracts the value away from you a little bit. It sort of puts a layer. The layer is this is the name of the variable. You use the name instead of the actual value, and then that sort of abstracts the value away from you, which can be very useful at times. The other type is functions. Right now, this might be a little bit weird because variables are really simple. It's just this sort of a equals b, or a equals value, name equals value. It doesn't have to be a single letter name like a or something. It could be my variable equals hello, whatever. Just some variable name, and then equals, which is the assignment operator, and it says we're assigning this value on the right to the variable name on the left, to the identifier on the left. And functions look like they have quite a lot more going on, and they do have a bit more going on. They're a little more complicated. Not terribly complicated though. Functions allow us to define an entire process and save that process under a name. And then every time we want to execute that process, a function allows us the ability to declare or define inputs into that function called arguments or parameters. And when we want to run that process that we define in the function, we will hand over some arguments, which are values that aren't specified during definition. That way, when we invoke the function, when we go use the function and run that code, when we invoke it, we can supply those arguments then, and then it'll say, oh, I know what to do with these input values. I'll take these input values in and run the process. And then at the end of it, usually, it's not required, but usually you'll have a return value. Same thing with inputs. Inputs are also not required. Arguments are also not required. You can define a function that doesn't take any parameters. It doesn't define any parameters. And then when you call it, you don't have to pass any arguments, right? Although usually functions will have arguments and they will have a return value. That return value is what we think of as the output. If you hear me talking about the output of a function, I'm talking about the value that it hands back, that it returns to me, quote unquote. Okay. So these are abstractions because in either case, they hold a value or a process, and they abstract whatever that value is away, and we can just we can use it and treat it as the name of that thing, that variable or that function. So it's a layer of abstraction. Control flow allows us to write code that will execute dynamically, depending on what conditions are or aren't met during runtime. Control flow will give us the ability to sort of, quote, make decisions or check conditions and respond to those conditions during runtime. So our 3 control flow keywords are if, elif, and else. Okay, if, elif, else, and then we've got iteration. And today we're going to talk about iteration. There are two, well, I shouldn't say main, they're not objectively the primary ways, but in this class, we're gonna use 2 primary means of iterating. They're both gonna be considered loop style iterators. Loops are not the most efficient possible way to do a lot of things. They sort of, when we talk about a loop, we're talking about something that repeats a process in a temporal order. That's a connotation that we have with loop. That's actually, I think, safe to say it's a denotation. When we talk about a loop, we're talking about an iterative process that happens synchronously or sequentially, right? So in time, the first iteration, then once that's finished, the second iteration, the third iteration, the fourth iteration. So this isn't getting into concurrent programming or parallel programming, parallelization. Python is sometimes smart enough to parallelize things kind of automatically behind the scenes for us. So it does a pretty good job of optimizing when it can. But in general, a loop isn't really set up for that, isn't going to run that way. But that's okay. You can learn about concurrent programming later, and the reason we're teaching loops is that they might be a little bit brute force sometimes, but they are very powerful. And by powerful, I mean they can solve a wide variety of problems. You can solve just about any problem that you need with for loops and while loops. There's certain problems that require something called recursion. If you know what that is, then you know what I'm talking about probably. If you don't, then that's a topic for perhaps a study hall or another day. So our iteration, and this is going to be, like I said, this is going to be our central topic for today. And it's going to be for loops and while loops. Cool. Could I give an example of how loops are used? Yes, I will. I'm actually going to save that. That's going to be the primary topic for today. I want to get through a couple breakouts, but we will be talking about that in depth. It's a complex. Okay, cool. Yeah. If you don't mind just waiting on that, I'm gonna get. I want to do a couple breakouts that we missed. That I kind of scoured through some of the prior lessons and thought these were good breakouts and would be good to give you all a little practice. I know we had a long weekend, so it'd be good to just get a little typing in. Oops, dang it. And just get into things this way. Cool. Okay. Oh, dang it. This is not gonna. You can see the other screen. Oh, you're kidding me. Hey, can people hear me all right? Can I get a thumbs up if you can hear me okay? Sorry, my Zoom just reset. I'm not sure what happened there. Hope we're not going to have more issues with Zoom. Okay. Okay, hopefully that'll hide away. Can people see the, if I drag the other window over the screen, can you see the other screen, the other window? Okay, I'm gonna take that as a no. Okay, good. I don't know what is with that. It's a very odd issue. Okay, let me get this breakout posted in. Okay, I think that's it. There we go, and we've got 4 minutes on the clock for this one. Somebody is asking about data flow diagramming. We're not going to go over that in premium prep in this course. It's more oriented around just teaching sort of basic practical tools to kind of get you off the ground and up and running. They might cover that in the actual DSI though. All right, cool. Go ahead and get in your answers. Go ahead and paste them in. Cool. Okay, we got some answers coming in. I'm going to go through a solution for this. You see the solution right here. I'm going to talk about kind of an approach that I want to mention, which is testing. Some of you're probably familiar with me talking about testing. You know how big I am on it. Okay, cool. So write a function that takes in a number between 0 and 999. Print out whether the number is a single, double, or triple digit number. Okay, so the first thing, oh, and I forgot, here's an edge case. So if the number is outside of the range, print a message saying that it is outside of the expected range. So the first thing that I recommend that y'all do, you have a new problem. I always like to have my problem statement just in my editor because I can kind of edit it around and have direct reference to it. The first thing we got to do in this case is think of a name for this this function. So let's call this digit digit length. Call it digit len. And the first thing that I want to do is write a test. So all I need for a test is a call to the function that I intend to test. I need to pass it a valid input. So in this case, we want to handle this edge case. So a valid input might be 1055, right? So 1055. Now this is valid input because my function is meant to handle this, right? It's sort of not the primary case, but it's an edge case, but it is meant to handle this. So in this case, I want to get back a message that says it is outside of the expected range. So I'm just going to copy this, and I should get a string that says the number, that's the it, is outside of the expected range. So I always like to check my edge cases first. So all I need for a test is a call to the function with some valid input that the function is meant to handle. It doesn't have to be the primary case, it can be an edge case. And then somewhere I've got to make an assertion about what that function with that input should return, right? And then let's try a few more. Let's do 8 should give me, so print out whether the number is a single, double, or triple digit number. Single, double, or triple. So this is a single, and then let's do a double and a triple. A double and a triple. So a double digit number is going to be like 55, and a 3-digit number is going to be like 555. I like to, oops, I like to kind of square everything off. It's just a stylistic choice. You don't have to put in all the spaces and format everything like that, but that's what I like to do. Okay, so I have a few tests here. The most it's most important that you write at least one test. If you don't want to write 4 for a small problem like this, I get it, it's fine. You don't have to write all of them, but at least write one. That way you can like run your code and check it. So there's a few ways I could do this. I think I'll just, oops. So notice I'm starting with the invocation of the function. I'm passing in an argument. But if I actually run this code, oops, I did not even start my thing here. If I run this code, I get this error. It says name error, name digit len is not defined, which is what I expect because I didn't even define it yet. But I do recommend that you start with the invocation, write all this stuff out first, and then get into the definition. If you want to do it in the opposite order and just like write a stub for the function, if that makes you feel better, then you can do that as well. So in this case, we're going to take in, well, I'll just call it dig for digit, and I'll run my code now that it exists. All these are returning none. So quick note, if my function doesn't have a return in it that's being executed, the function will always return none, right? So this pass is just a placeholder. It just says, hey, don't worry about it. Don't do anything. It's just like pass. The reason I put a pass in here is if I don't, then I get this error. It's an indentation error, and it says expected an indented block. So anytime Python expects an indented block, there has to be something indented in there. In this case, I'm putting pass as just like, I'll come back around to that. Don't worry about it now. I'll come back to it. So, okay. So what occurs to me is to say, we could cast the digit to a string. So I could say dig stir equals, let's do this, dig stir len equals len stir dig. Okay, so I'm taking my digit, I'm making it into a string, which is going to give me a string of that digit. It's going to convert it to its characters in a string format, and then I'm going to get the length of that string, and that's going to tell me how many digits are in my string, right? So, and then I'm saving that under dig stir len. And then from here I can just say if dig stir len equals 1, lf else, so this will be the else, and I'll do these one at a time, so I'll just comment those out for now. Else, oops, elif, there we go. So we'll do this. So if dig stir len equals 1, we'll do single, oops. If it equals 2, we'll do double. If it equals 3, we'll do triple. Else, we'll do our edge case here. Okay, cool. So I expect my edge case, which is what I see here, and then single, double, triple, which is what I got. So I look at my output and it matches the pattern of my expectations. So I'm good to go. So this function should work. Cool. I want you to take note of this pattern of testing where you start with your tests. You don't have to like I said, you don't have to write a bunch. Just write any that are obvious. They don't have to be like done up and fancy. I usually write tests that are slightly fancier than this, but this is just a print and a comment, right? This is just Like I'm printing whatever this is going to return. I'm passing it an input, and for this input, I'm just saying this is what I expect in the comment. That's all it is. Cool. Could we have used the range function to execute this? Range. I'm not exactly, I won't say no, because, you know, somebody might think of something that I didn't, but I don't know how to, if you can use range for this, the answer is not obvious to me. I think no. My suspicion is no. I don't think we can use range for this. But kind of interestingly, len is a very related function to range. I think about it as kind of the opposite of range. If you think about range takes in integers and uses those integers to return an iterable equal in size to whatever those integers described, right? So its inputs are integers, its output is an iterable equal in length to the, you know, the range described by the integers. So integers in, iterable out. Len takes in an iterable and returns an integer. So iterable in, integer out. So a lot of times, if you're thinking about how do I use range, and you're like having a hard time making it work, you might consider using len, and vice versa. If you're like, oh, I could use the len function for this, and you're like, wait, but how would I do that? How would I get this all to fit together right? Maybe consider the range function. You know, so a lot of times if I think of one and I get confused, I'm like, wait, what about using its counterpart? So you can think of range and len as kind of secret counterparts. They're not really obviously counterparts, but they're, if you kind of think about them, they are kind of related. I think of them as related. So I think probably what you're observing is valid as well. Oh, you're talking about checking in different ranges. Yeah, you could do it that way as well. Yep. See, that's what I mean, you know, like you might think of something that I didn't. Okay, cool. Yeah, there's a number of different ways. So they solved this in a bit of a different way. They did this, you know, if the number is less than 0 or the number is greater than 999, then they return the edge case. And in this case, they're printing. I know some of our material, oh, and this needs to be fixed. That's just an error. Something got messed up there. I know some of our material will have like functions in it where you print something instead of return. Aside from those places, I'm kind of trying to go through and like find all those places and kind of change them into returns. But you know, in reality, your functions will almost always have returns instead of prints inside of them. And then if you want to print something, you'll print the function call, which means you're printing whatever it's returning. So, okay, cool. Yeah, all right. On to the next one. So I have a little challenge. I wrote a little bit of a challenge, and this is why I wanted to talk about testing. I wrote us a little challenge that we can do. It's just a little breakout. And this one's going to be oriented around the tests. Okay, oops. Okay, so this is a pretty simple function. So the breakout here is 2 steps. One, first thing I want you to do is write the test. Again, there's a little bit of a, you know, you have a little bit of a liberty in terms of what you want to give as an input. And then for a given input, given the constraints of this function definition, you'll have an output, and I'll leave it to you to determine what that should be. So it doesn't have to be structured exactly like mine. If you want a structure that's consistent, then you can use the structure that I'm giving here, where you just print out the function, give it an input, and then leave a comment on the end that just says that's what you expect that function to return with that input. So I'll put 4 minutes on the clock. First step is get the test in and just put that in to Slack. And second step is to write the function. Okay, cool. All right, we can call this here. So what I did while you all were doing that is I just wanted to show, oops, let me make sure. Check. Okay, cool. Sorry about that. So I just wanted to show sort of a variation on testing. So I wrote a function whose purpose is to test the other function that I haven't written yet. So you might think, oh, well, I'm starting with a function definition, but this function definition's purpose is to be sort of the pattern in which I want to test the other function. Now this is a really simple function in this case, so it's a simple test. But once we start getting into more complicated functions, you may want to write functions whose purpose it is to run your testing logic, so you don't have to repeat it every time, and then every time you want to make a new test, it's easy to just copy that function and, you know, paste a new call to that function rather than like rewrite the whole, you know, logic. In this case, it's just 2 lines, but in other cases, it might be 5 or 6 lines or 10 lines to run a test, right? And then raised to power, def. This will take in, I'm just going to call it A and B and return A to the B. True, 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 83264. All right. So it passes my tests. So you don't have to, I'm not showing you this because I'm trying to tell you, you got to write all your tests like this in the fancy way. You don't, but it's just a variation on the theme. I want you to be creative with testing, you know, so you can come back and watch this video, see what I'm doing here, reason it out. If you're really curious about it, feel free to DM me. I kind of like talking about testing, so, and teaching people about testing. So I don't mind talking about it more, but yeah, just want to make it clear, like, I don't expect you to memorize this right now, just to see that, you know, you can be creative, you can just think about the problem. How do I verify that this is actually going to do what I need it to do? We got a question, could that be tested with an assert? Yes, you could also use assert statements. I'm not getting into asserts because I don't want to, they kind of add another layer of complexity. And I think asserts go best with like error handling techniques, which I'm specifically avoiding in premium prep. But all that stuff, if you want to learn about it, yeah, feel free to DM me. It's interesting stuff. Cool. All right. And shoot, we're almost halfway through. I had this other breakout. We dove so deep into the other breakouts. I thought this was going to be like the first 30 minutes of class, but I think I'm going to forgo this last one. I want to get into loops. Okay. Somebody's asking for a concrete example of loops. I'm sorry to keep you waiting. We will get into loops now. In this, we're going to cover some sort of looping related topics. We're going to cover traversing a list. We'll get into what that is. The accumulator pattern, which it is difficult to understate the importance of this. I know it's just another bullet in the middle of another bulleted list, but everything that we are learning is going to kind of come together when we start writing accumulator patterns, and hope that will develop over time. You'll see what I mean. But Boolean flags, which are related to accumulator patterns, just I think about them as accumulators with Booleans. They have a special name because they're Booleans. And list accumulation, using loops as filters, and then break, continue, and pass are some keywords. I already talked about pass. Every programming pedagogy I've ever encountered teaches break, continue, and pass together. And it's funny to me because break and continue are related, and pass is kind of not related to break and continue. And I just want to say this right now, so when we get to this, you know, there will be context, but pass's job is very simple. I gave an example of it, you know, when I was just writing the function stub for that previous problem. When you see pass, it's tempting to think, oh, this must do something subtle that I can't yet comprehend. Pass literally does nothing. Its job is to be valid Python code that just doesn't do anything. And you might think, why bother, you know, writing in a keyword that's just ignored, that just doesn't do anything? The reason is the example that I gave before, def my function. So imagine I have some project and I know I've got to write 10 functions. You can see my syntax highlighting is getting messed up already. Let's do this. Let's say we'll just number these just because we're lazy, or I am. Okay, so this will be function 1, function 2, function 3, 4, 5, 6, 7, 8, 9. Okay, so I've got a project, and I'm like, okay, I know the parts that I need to build. So I'm just going to name those functions, and I'm not going to build them right now. I'm going to kind of go through them one by one and build them. Probably in a more realistic workflow, I've maybe built out the function heads for these and the tests. That's a pretty fairly realistic, feasible, in industry workflow, or something that you might see, something like that. So you'll start with just the function heads and the tests. So I can't do this. This is not valid code. If I try to run this document, I'm going to get this error. It says unexpected an indent block. Like I said, Python absolutely requires that I put something in there. Enter pass, which is our way of saying, hey, Python, don't worry about it. I got it. I know what's going on. I meant to put that there. It's intended to be a function that is not fully defined. And it's like, oh, just so long as you meant that, pass is sort of your way of reassuring the interpreter that, yeah, I meant to do that. Just move on. Don't worry about it. So that's pass. Okay. I know it's a long explanation, but it's like it's hard to like justify the utility of something that literally doesn't do anything, So, okay, cool. Let's get into loops. We've got some breakouts for lists. I think we'll come back and do these if we have time. We'll do those. Okay, so loops. So loops, very simple idea. They just allow us to repeat code dynamically. And by dynamically, I mean the number of times that some body of code is repeated is determined at runtime, right? So, or maybe it's determined at the time we're writing it. Maybe it's baked in and fixed. But it allows us the ability to repeat code without literally like typing the same code out 10 times. And I'll give you an example. So let's say I have a list and it's an empty list, and I want to append the square of every number between 1 and 5. I could say list.append 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, right? This isn't very good. I mean, this isn't very satisfying code. I'm just like typing this out as many times as I need it, right? What if I don't know how many times I want to repeat this operation, right? Can make that a little difficult. So let's look at this a different way. I want to repeat this append number to the second power, number squared. I want to repeat this line because essentially that's all I'm doing. I just need some source where I can get each number between, the minimum and the maximum of whatever range that I want. And I can use range to help me out with this. So I'm going to write a for loop to repeat this line of code. I'm going to say for, and then I in range. And let's just say 1 to, we'll stick to 1 to 5. Okay. Excuse me, num. We'll do that. For num in range 1 to 5. Now, there's a little bit going on here, but you know, before you get into like dissecting, you know, like the like massive text that I just kind of threw at you and like what each part does, kind of think about how this reads as English, right? For a number in a range 1 to 5, right? So what this is going to give me, and this might not quite be obvious, but this is going to repeat this code as many times as there are objects in whatever iterable I pass here, right? So the anatomy of this is we have the for keyword, and I'll kind of straighten all this out like this. Then an identifier, which is identifier is a fancy word for variable name. It's the name part of a variable, right? So notice, you know, this isn't a variable in the sense where I'm being like, I'm not saying like num equals 1, then num equals 2, then num equals 3, then num equals 4, right? There's no equals here, but that behavior is essentially happening due to the for loop, right? Then we have the in keyword, IUN, and then some iterable. We'll just call it iterable. So, well, I don't need that keyword. We'll do this. So I'll surround the keyword parts in backticks to make it very clear. There we go. So for identifier in iterable. So identifier is any name, any variable name. If you wanted to for variable name in iterable, you could read this as that if that helps. Identifier is a little more formal word. So for identifier in iterable, and the iterable is any object that can be iterated through, as defined by being able to stick it in a for loop like this, right? So an iterable, you know, you'll learn which objects are iterable over time. Range is iterable, lists are iterable, strings are iterable. We haven't gotten into dictionaries yet, but dictionaries have iterable aspects about them. So do sets and tuples as well. We'll get into those data types later as well. Won't range 1 to 5 only go up to 4? Yes, indeed it will. So in this case, this identifier is going to represent each number in this range, starting at 1, and then so this repeats this process. Like I said, it repeats this. And no, it's not much of a process. It's kind of overblown to call this a process, but it's just a one-line process. It just repeats this one line of code, so we don't have to duplicate it and have a bunch of lines that look the same, right? So it's just going to repeat this one line of code, and it's going to repeat it 1, 2, 3, 4 times in this case. So since it repeats it that many times, and it repeats it that many times because that's how many objects there are in this range, and it's going to assign each value in that range, one after the other, in order to the identifier, right? So if I do this, print list like that, I get 1, 4, 9, 16. And then if I, let's see, let's just print out num, just like that. So I get 1, 2, 3, and 4, right? And if I were to if I were to, print a list of this range, I would get a list containing 1, 2, 3, and 4, right? So you can see in this loop, hopefully you can see in this loop, right, each number in this range is being assigned in order, right? I want to make it clear, like, because it's hard to word this in a way that makes it clear, like, it's not happening all at once or in parallel. You know, maybe it is behind the scenes somewhere, but we don't need to think about that. It's happening. The way we think about it is it's happening in order, one at a time, right? So num at any given time only has one value, and that value comes from this range. It's a number between 1, 2, 3, and 4, and it's just, it starts with 1, and then it's 2, and then it's 3, and then it's 4, right? So it has that ordered nature to it. Cool. For all numbers in range, is that how it can be? Yeah, for all the numbers in the range as described by the the arguments that I'm passing to range. Exclusive for the last time. Why use for rather than while? Ah, okay. This is an interesting kind of philosophical question. So, I'm not going to talk about while loops much today. I'll just mention this. If we want to talk more about while loops, I'll take questions after class. But this is a good question. I'm sure a few people are thinking this. So I talked about there being two types of loops, and we are going to focus on for loops today. While loops are capable of solving any problem that I can solve with a for loop, I can also solve with a while loop. Some problems that I can solve with a while loop, I can't solve well within the bounds of what a for loop really is supposed to do. There are kind of ways of really bending the capacity of a for loop to kind of get it to do anything you want. Although at a certain point, it just makes sense to use a while loop. So that being said, since while loops can solve all the problems that for loops can solve, plus certain problems that for loops aren't really well suited for, why start with for loops? The reason is, some of you might be familiar with the idea of an infinite loop, right? Where a computer program gets into an infinite cycle of looping that never stops. While loops burden you with controlling when they stop. A while loop will not stop unless you tell it to. It checks a condition. As long as that condition is true, it just keeps going forever. And sometimes you want that. Sometimes that's useful, and that's something that they can do, and that sometimes can be useful in a way that for loops are more limited. But the reason we start with for loops, and the reason we tell you always use for loops whenever you can, is they handle the stopping condition for you, right? So I don't need to write any other logic to say, hey, just to be sure, once you get to the end of this iterable object, you're going to break, just so you know. Whereas if I were writing a while loop, I would have to do that. The responsibility would be on me as the person writing the code to like engineer, okay, under what condition should I stop looping? When does this need to end? In my experience, most of the problems that I've encountered follow this kind of pattern where I have some set of things that has a limit, and I know what that limitation is. I know how many things I have to process. In this case, I have 4 things to process, just 4 numbers in a simple range, 1, 2, 3, and 4. So I can just stick that in a for loop and have that processed nice and easily. More control over the parameters in for loops. Yeah. Yeah. For loops kind of make it, they take a little control away from you, but they make most of the kinds of jobs that you need a loop for, way easier. And then the times when you can't use a for loop, then you have to use a while loop. But yeah, it's sort of it's a power versus responsibility thing. Like while loops are very powerful, but they come with the responsibility of managing every little detail of looping, whereas for loops kind of manage that stuff for you, but they, you might need every little bit of power you can get. You might need to like do something different, and that's what for loops are good for, or while loops are good for. Anyways, okay. I said I wouldn't get too into it. Here I go. Good question though. All right. So this is just a basic example of for loops. Let me give another one. I could basically, I'll just kind of write this from scratch. We'll do this. Let's do list equals an empty list. So in this example, I iterated through a range, and just to prove that this, this range is not, a mandatory part of the for loop, we can iterate through anything that's iterable. So let's say I'll call this square list, and I'll have another list called list equals, and this will just be a list of numbers 5, 3, 7, 9, 15, 22, 3. Okay, so let's say for num, and remember this is an identifier, so it's an identifier like LST or square list. This is just something that I get to name. I get to call this whatever I want. There's a convention around calling this I. I suggest you follow that convention when the number in the or when the element in the thing you're iterating through is a number. Generally, I'll call that I. And that's the convention. For now, I'll be semantic and I'll just say for num in list, LST, right? So this is my source and this is my target. And then I want to do square list dot append num squared. Okay, cool. So if we look through here, right, we have a list, just got some random numbers in it. We've got an empty list, which is our target. Now I said I would build up to accumulators, but this is an accumulator pattern. It's a very simple one, but it's got basically everything for an accumulator pattern. So you can see probably why it's called an accumulator, because I start with something empty, and as I repeat this append, I'm accumulating into it. So we have accumulator patterns. You can think about there's like different nuances for the accumulator pattern per each type, right? So there's integer accumulators and float accumulators and Boolean accumulators and string accumulators and list accumulators. So for every data type you learn, you're going to kind of want to learn an appropriate accumulator for that type, and they don't differ tremendously. This is why we call it a pattern. The overall pattern is the same, right? Start with something that's probably empty. There are times when our target, our accumulator target, will not be empty. So start with something that's empty or zero, probably. Iterate through some source of data. It can be numbers or strings or lists or anything. Iterate through some source, perform some process. In this case, we have this really simple one-line process. The code in the for loop can be however many lines long that you need. And of course, notice just like a function or an if or elif or an else, the for line ends in a colon, and then on the next line we indent, and that tells Python what code I intend to repeat as the part of this list. So the reason it prints this out once is because I have print square list tabbed back on the same level, right? It's not tabbed in underneath. It's not tabbed inside of, under and inside of the for loop, right? If I did tab it, actually this would kind of give you a picture of what's going on. You'll see the accumulation happen, right? So, obviously we start with an empty list, then we append, and then we print. We append 5 squared, which is 25, and then we print, and then we run this process again. We do the append, and then we print, so we got 25 and 9, and then we do the process again. We append, and then we print. We've got 25, 9, 49. Then we append and print, and we get 25, 9, 49, 81, etc. Right? So you can have as many lines of code in here as you want, and it's not uncommon to have an if inside of here, or 2 or 3 or a dozen or whatever. So let's do something. Let's change this up a little bit, and let's say like, let's call this let's call this ACC list for accumulator, right? So I'm going to say if the number, let's just say if the number is less than 8, we will square it. Else, we'll append the square root. Cool. Something we could do. So what this is saying is it's going to run a different append operation depending on the size of the number. If it's less than 8, we're going to square it. If it's 8 or greater, then we're going to append the square root of that number, right? So if we look, 9 is going to be the square root. Square root of 9 is 3, right? Square root of 15 is 3.87, etc., right? Square root of 22 is 4.6904, etc. And then we have a 3, so that one's less than 8 again, so we're going to square that and we get 9. Oh, we got some comments here. Could we finish the for loop example? I got confused with discussion about while loops. Okay, yeah. Yeah, while loops are a whole other animal. Sorry about that. Yeah. Okay, so this is basically basic usage of a for loop. You can see, hopefully you can see that at the end of the day, basically the whole point is to just repeat the code indented under it as many times as there are elements in the iterable that we put in the final part. And another purpose of it is to extract each value from an iterable one at a time, right? So another way of looking at this is for num in list is like saying, okay, I've got a lot of numbers in this list, and it'd be kind of nice if I had a way to assign each number in order, one after the other, to a variable, in this case num, just in order, one after the other, right down the line until we get through the list. And that's all it does. So we assign each number in the list lst to num, and then that num holds the number one at a time, and then we repeat this process for each value of num. Cool. Okay. Want to do a little bit of a sort of a system check. How are people feeling? If there's any lingering questions, feel free to put them in there, or you do a temperature check, thumbs up or thumbs down if you're feeling good. about like sort of looping basics with for loops. Is an append, we got a question, is an append supposed to add to the original list? It only prints the new list. Yeah, exactly. So if we look here, right, I create this list called LST. And why don't I give this a better name? LST is so generic. Let's call this SRC for source. We'll call this source list and accumulator list, right? So our source list is the source of things that we're going to iterate through, right? And then I have this empty list on which I intend to accumulate, right? We have our for loop, and then I'm calling append on the list that's the empty list. I'm calling it on the ACC list, right? So this append is essentially unaware of the SRC list. You might think, oh, well, you know, how could that be? Because we're passing num. Num is from the for num in SRC list, but you know, that's just extracting a numeric value, and we're just using the value in that identifier to figure out what we should append to the empty list. Does that make sense? I would say also to the response there, append is a method for lists in general, right? And I'm just calling the append on the list that's empty. And since I'm saying ACC list dot append, then it's not going to append to source list. Cool. Seems like that's making sense to folks. I'm not seeing the original poster thumbs up on that, but I'm hoping, is that making sense? If it's not, feel free to like ask any follow-ups. I don't mind going over this. Okay, you good? Cool. We will be, I promise to, I know for loops can be, they can feel like a lot, but like we will be revisiting this a lot. You will get plenty of practice with this, so worry not. Okay, so traversing a list. I did this all out of order. When we talk about traversing a list, it's actually what I'm doing here. It just, you know, traverse to walk through a list. You could think about like we're walking through this list, we're traversing this list, going through each element one at a time, you know, capturing each element one at a time in the identifier called num. So that's list traversal. Cool. Okay, cool. So this is kind of a fun breakout. I find it fun because I am a real nerd. Let me do this like that, and we'll go right there. Okay, there we go. There's the breakout. And I'm just going to put a few minutes on the clock today. Let's put 4 minutes on the clock for this one. I just thought maybe this might be worth clarifying. You don't have to do this as a function. Feel free to if you want, but you don't have to. You could just write a loop. Oh, also, you don't have to not do it as a function. I saw somebody just paste a function and then delete it, so it's just up to you. All right, go ahead and put in what you got. Cool. I'll give a quick solution for this. Well, we'll forgo that. So I'm just gonna print hello there. What am I doing? This has got to take in, okay. Given the following list of letters, create a function that goes through each letter. Okay, gosh, I just got right off track immediately. That's what I did. Okay, so this is kind of giving us a test right away. Go through each letter and print the letter if it's a vowel. So what I'm going to do is a bit of a variation. I'm going to append it if it's a vowel and return a list. So let's say vowels of char list. We'll call it vowels of def. Vowels of, we'll take in some letters, and I'll say ACC equals empty list. And I'll say for CH in, CH is short for character, I'll just call it CH. For CH in letters, if CH in, and I'll check a tuple containing, actually I don't need to do a tuple, I can do A, E, I, O, U. So if CH is in this string, we know it's a vowel. Also, perhaps, we use a different list and we've got like a capital O in there or something. So maybe I want to do ch.lower. like that. So we get the lowercase version of ch, and check if it's in here. Another way around that same problem is you could do AEIOU and then just include the capitals AEIOU. Let's just do that. That's kind of simpler. So if ch in that string, then I know it's a vowel, and I'll say acc.append ch, and then I'll return acc. Oh, great. There we go. O and I. Solution, we've got a whole thing going on with the helper function here, which is going to tell us true or false if the letter is in that list of vowels. Okay. So given two arbitrary lists, okay, write a function that finds common elements between them, store these common elements in list. So I suggest with this one that you start with a test, right? We have two arbitrary lists, and you could think what those two arbitrary lists are and what the return value of this function should be. And we got a question here. I'm going to do 6 minutes for this one because this is a good one. We got a question here. Where does the dot lower go if going that route in the previous breakout? If I used dot lower, which is what I would tend to do, that's my preference. I would use dot lower right there. So I would check the lowercase version of ch, and I would see if it's a member of the string AEIOU. Sure thing. Are we assuming both lists are the same length? Write a function that finds common elements between them and store these. You could add that as a constraint, but I think you could write this solution in a way that it would handle lists of differing lengths. I'll leave it up to you if you want to add that constraint or not. Okay, cool. Go ahead and get in whatever you've got. I obviously decided to spend my time writing tests. And I'm trying to go like a little over the top here just to show you, there's a wide variety of ways that you can test things. So let me actually think of some test cases now. So I have this function that's going to give me this kind of nice, cushy formatted test here. And I could say something like I could say like imp equals L1, L2, and exp equals exp. There we go. Yeah, okay, so if I do this, if I say, let's say I have a list of 3, 5, 7, 4, 5, and a list of 2, 0, 5, 4, 3. Okay, so let's see what I have in common. So I've got a 3, I've got a 5, yep, I've got a 7, got a 4, okay, so it looks like I've got a 3, a 5, and a 4. No 7? Right, no 7, oops. Okay, so 3, 5, 4. So the expectation for this is going to be a list containing 3, 5, 4, and I wanted this sorted, so why don't I do 5, 3, 4, 5 like this. I do have 2 5s in here, and I don't want duplicates, so we'll operate under that constraint. Okay. So from here, I think we can do for, somebody asked too, and I meant to do this as well. If we could, if the lists have to have the same number of elements, so they don't. So let's do something different like this. Let's say I add a 7 in here. We'll actually add 7 like that. Okay, cool. So now we have, this one is asymmetrical. The lists are not the same. Okay, so now we can just say ACC equals, this is our accumulator, start with an empty list. And I always like to just kind of write out all the things that I know I'm going to do, or I'm pretty sure I'm going to do at least. We'll start an empty accumulator and just return it. And then I'm going to say for element in L1, EL. I'm using EL because I don't know if it's going to be a number or a string. Actually, this would work with strings as well. It's just common elements. They don't have to be numbers. So I'm just going to say for element, EL to me is short for element. Sometimes I'll use ELE. So for element in L1, and I'm choosing L1 because it, I think, doesn't matter which one I choose. And then I'm going to say if EL in L2, then acc.append EL. So if it's in both, then we'll append it. And I also only want to append it and, yeah, I'll say and L not in ACC. So if the element is not in the accumulator, then I want to append it. And this will prevent duplicates if I say, if I'm checking if it's not in there, right? So if it's already in there, element L not in ACC, this phrase L not in ACC will be false. So this and will make that condition false, and we won't do an append, right? So if the element is in is in L2 and it's not in the ACC, then we'll append it to ACC. If it's not already in ACC, basically that's saying. Then we'll do that. And then I wanted to do this sorted, so I'm just going to return the sorted version like that. We could do that. Okay, so here's my fancy schmancy little tests. I have these two tests, and it looks like true, 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 right? So I decided, like, I want to build this in such a way that it doesn't matter which order the lists get passed in, right? If I passed in list A and then list B, they should have the same elements in them regardless of if I do A and B or if I do B and A, right? So if I built my function in a way that it gives me a different result depending on the order of the elements, I know I kind of did something wrong. I'm probably not doing this right. So I decided, well, if I try to switch the inputs around, that'll tell me whether it's getting the right result. So you can see I'm getting true and true and true and true. So I'm getting positive signals from the test. So it tells me I'm passing the tests. Now there is a bit of an optimization. What if, now this just works. This just totally works for lists of different lengths. They don't need to be the same length. But you could imagine a situation, maybe I want to see, maybe I have a list with 50 elements in it and another list with 5,000 elements in it. Well, I'm iterating through L1, so this is going to loop through whichever list L1 is. But it actually doesn't matter if I iterate through the shorter or the longer of the two. I'll still get the correct answer, but it does matter in terms of how many numbers I'm going to crunch, how many cycles of this loop I'm going to run. I would much rather, if it's going to work the same, whether I go through the list with 50 elements or 5,000 elements, I'd much rather go through the list with 50 elements. I'd much rather write my function to do less work if it's going to turn out the same anyways, right? So let's do something like this, shorter list. I haven't created shorter list yet, but that's okay, we can create it. So I could just say shorter list equals, we'll just do this. If len L1 is less than len L2, then shorter list equals L1. Else shorter list equals L2. And that way I'm always iterating through excuse me, let me try that again without the tongue twister. That way I'm always iterating through shorter list. And this logic is going to determine which list is shorter. I just compare the lengths. And if this is true, then I'm going to assign it to the one that's shorter, which is L1. And if it's false, then I know they're equal in length or L2 is shorter. So I'm going to assign L2. And it doesn't matter if they're equal in length, it doesn't matter which one I pick. So I could do less than or equals. It doesn't matter. So it doesn't matter which one I pick if they're equal in length. So I'll just go whichever one is convenient. In this case, that was L2. So we go from there. We got a question. How will sorted work with ints and strings combined? It won't. Interestingly, you can sort a list of strings and it'll work. It'll alphabetize that list of strings. So if I have a list of words or substrings or sentences or paragraphs or whatever, it'll alphabetize. It'll actually, technically what it does is it places everything in lexicographical order, which is a superset of alphabetical order. Lexicographical order includes alphabetical order, but it also has an ordering for that includes numeric values and special characters and things like that too. But you can think about it as alphabetizing. If I sorted a list of strings, I would get an alphabetized list of strings. If I sorted a list of numbers, I would get a list of numbers in ascending order. If I sort a list of numbers and strings, I will get an error. So you can't actually sort a list with this sorted function that contains numbers and strings. You have to make sure that it's one or the other. If you can think of a sorting algorithm, that works by making an assertion about how um, the word apple should be sorted against number 37, for example, you could do that, I suppose. I think what you'd end up with is something like lexicographical order, but yeah. Anyways, good question. Yeah, you're welcome. Cool. Okay, let's see what their solution was. Okay, so get common elements takes in list 1 and list 2. We've got our output, which is our accumulator for item in list 1. That's basically the same for loop I'm writing, different identifier names, but same idea, just for an element in the list. Then if item in list 2. So if it's we're extracting the item. Oh shoot, I realized a hole in my logic here. I'm sorry. I need a longer list. Dang, I totally omitted that. Longer list equals the other one. 2. Okay, we'll just pretend that I totally caught that the first time. Okay, so iterate through there. This is just checking if it's in the other list, if the item is in the other list. So the item is coming from list 1, and we're just seeing if item, which is from list 1, is also in list 2. And I'm doing this little bit of a juggle with the shorter and longer list. So, I pull an item from whichever is the shorter list, and I see if it's also a member of the longer list. And then here they have this nested if, which is in this case identical to an if with 2 conditions separated by an and. It's just kind of 6 of one, half a dozen of the other. If it's not in output, that's the same as that and, that second condition. Then append it to output and return the sorted output. So it's essentially, just a little bit slight variation on the solution that I gave. I would say it's logically the same way of thinking about the problem. I've said this before, and I'm going to say it again, that multi-line ending looks so sick. Multi-line ending. I'm not sure what that is. Okay. Oh, multi-line editing. I'm sorry, oh, that totally says editing. Oh, I'm having I'm a little light on sleep, and my dyslexia just goes into total overdrive when that happens. So, like, ending, what does that mean? Yeah, the multi-line editing is the best. You can absolutely do it in VS Code. VS Code actually has a few things that make it a little better. I won't tell you my shortcuts. 1, I'm using Linux, which you're probably not using. 2, I'm using Atom, which you should really use VS Code. 3, I customized all my shortcuts, so even if I was using the defaults for my operating system, they wouldn't be the same as what you're going to use anyways. Go look up, do a Google search for, oh gosh, I meant to link something to this. I'll link it after class if I remember it. Otherwise, you can go do a Google search for like best VS Code shortcuts, multi-line editing in VS Code, something like that, and you'll get a ton of good resources, or they're really easy to come by, good resources for that with VS Code. So. You're using Arch. Nice. Okay. I spoke too soon. I am using, hotkeys, just keyboard shortcuts and stuff. Cool. Accumulators are important. So we've talked about accumulators. You know, these examples. This is the thing, you know, I can't, like I said, I cannot overstate the importance of accumulators, but I think part of, uh, part of the difficulty in describing the centrality and the importance of accumulators is they're actually kind of simple. If you look at this code, it's not, you know, it's not a dozen lines of code and, you know, super weird stuff. You know, let's just look at this. Now, I made my solution extra fancy with a test function that's like way too fancy, just to, you know, just because, right? But this is the core of the accumulator. We have our empty thing, our target, and we run through some source with a for loop. You know, if you understand the for loop, you know, this code is not um, super complicated. You know, even if you're still learning this stuff, it's just a few lines of code, but it's an accumulator pattern. And it's hard to see like, well, how can, you know, how can something that's just a few lines of code, how can that pattern be that central? And the way I think about it is there's a lot of things that you can do and should do in a different way than an accumulator pattern. When Tovio starts taking over classes, they will be talking about, I'm lacking on the term that they use for their um, analytic approach. That's they're going to talk about something they call the analytic approach, um, which has to do with like different ways of problem solving, right? Different ways of approaching problems. So there's a lot of problems that like are probably better solved with a closed formula. But if you don't know the formula and you're researching and you can't find a formula for something, odds are pretty good you can just figure it out with an accumulator pattern. It is weird. Um, like it, like when I realized the power of the accumulator, I was like, oh, like this is kind of, you know, so at the core of so much is the accumulator pattern, right? You think about how you would build a len function or a sum function, or a lot of the functions that you'll encounter. A count, you know, later we're going to talk about the count method for lists and strings and stuff. As you encounter different functions, think about, you know, could I build that? Could I build something that does something comparable? And a lot of times the answer is, yeah, you just use an accumulator pattern. So that's kind of the cool thing too. There's a lot of functions and methods and built-in tools. There's this huge vocabulary of things and tools and stuff that's built into Python. And when you're a beginner, it can seem overwhelming, but this is why I'm telling you, like, get good at the accumulator pattern because it will fill in those gaps before you know, even a good example. Um, I learned a new string method a couple months ago called zfill, and I, you know, I wasn't aware that it was a string method, and it accomplished a task that I would do manually by just building accumulator patterns to accomplish this task. You don't have to go out and learn zfill, and it doesn't matter what it does. But the point is, I went, you know, several years doing this task that I would do fairly often in a number of, you know, my coding experiments and projects and stuff manually, and I never really thought about it because it was, you know, I'm just like, oh, I'll just write an accumulator to do this, and I'm like, oh, well, there's a method for that, you know, so it's cool. This will fill in the gaps of the vocabulary that you don't have yet, that you haven't developed yet and haven't grown into yet. And, you know, that vocabulary, learning all those tools takes time, and that's fine. But yeah, I mean, you can just kind of do anything with this simple little pattern. We've only got a few minutes left. Let's talk about, we'll kind of get into some different kinds of accumulators here. We're gonna need, I think, a second day on loops, which is okay, I think, for loops. So sum accumulation or integer numeric accumulation, I would probably retitle this numeric accumulation, just kind of be a catch-all. Let's see. Okay, let's do something like this. Let me get a source list. Let me get another source list. Here's a source list. And I'll say for element in source, oops, list. Let's say I want to count, I want to know numbers greater than numbers greater than 5. So I want a count of numbers that are greater than 5. So we'll say numbers greater than 5 is 0, because right now I'm assuming there are no numbers greater than 5. We'll just start it at empty or 0. And I'll just say for L in the source list, can you see where I'm going with this? Think about it for a second. I'll type it in. This isn't really a proper breakout, but think about it. You probably already see where I'm going with this. If L is greater than 5, then I'll increment the value here, right? So I'll use plus equals to 1, like that. Yeah, plus 1. I'll add 1 to it, exactly. Bingo. So that'll count all the numbers that are greater than 5. So I'll print numbers greater than 5. Oh god, I should call this count of numbers greater than 5. I'll give it the long name. Okay, count of numbers greater than 5. So there's 4, and let's check that, right? 5 is equal to 5, so it's not greater. 1, 2, 3, 4. There's 4 numbers greater than 5. Cool. So that's an example, right? This is what I'm talking about. Let's just let's do something like this is our accumulator. So it's important to, like with every type, to kind of like understand how accumulation works with that type. We got to do plus equals here. There's no append, right? It wouldn't matter because append doesn't really apply. We're not trying to add in an element. We're just trying to count something, right? So we could modify this value in a number of ways. We could do like times equals. I'll give you another example. One you're going to see a lot, def factorial. We'll take n prod equals 1 for I in range. We'll start at 2 up to n. We'll include n, so we'll say n plus 1 like that. And then I'll prod times equals I and return prod. And that'll be a factorial algorithm. We start prod at 1 instead of 0 because since we're multiplying, if we introduce any zeros, everything's going to be 0 from there on out. We could start the range. We don't start the range at 0 for the same exact reason. Again, if we multiply 1 times 0, we get 0, and then everything we multiply by that 0 forever is going to be 0. So we don't want to start at 0. We could start at 1, but prod starts at 1, so our first iteration of the loop is 1 times 1, which we already know is 1. So we can just skip that. We can just start at 2. So that's why I start the range at 2. I want to include n, so I'll do n plus 1 here, and then prod times equals, right? So this is another numeric accumulator. So this is what I mean, right? This is a counter. Maybe I should call this counter. Right? This is a counter style accumulator, but it's not the only thing that we could do with an integer or a number as an accumulator. Similar patterns will be used for floats as well. And as you code, as you think about solutions to problems, think about the accumulator pattern. Remember me saying, write your tests, consider using an accumulator. You won't use it for every single function or every single solution ever, but you will use it for a lot. It will come up a lot, the accumulator pattern. So yeah, and just think of various different ways. You can be creative on various ways you can alter different objects. Cool. All right, that's all that we have time for today. We're a little over time. Sorry about that. Hope I'm not keeping anybody up too late. Y'all have a good rest of your night. If anybody wants to stay on for questions, let me just stop the recording and we'll get into that.